day. Heard the people speculate. Bellies cringing, eyes are twinging. Oh, what a messy Christmas day. After a time of half a year, kernel patches cause some fear. Error traces, warning chases. Oh, what a messy Christmas day. Reasoning was not all sane. That Kaiser was merged these days. Posted by an engineer. Leak privilege memory. New Year brings a higher pace. People try to replicate. Twitter people posting code. Does this break the embargo? Embargo, embargo. Meltdown and Spectre, then go clear. What a start in the new year. No more Christmas holidays. Messy, messy Christmas. Messy, messy Christmas. Oh, what a messy Christmas day.
Morning. What are you all doing here? Shouldn't you be working? I mean, come on. I will talk today about performance of computers. Who likes performance of computers? Fast computers? Yes, everyone likes it, right? And of course, we have to put some acknowledgements here because we didn't write the music, of course, the photos and other stuff, and also the results from this talk. I mean, other people have contributed there. But let's go back to performance. Performance. All of the performance that we have in modern computers, all of this started with the Pentium Pro. This was 1995. That is a long time ago. I was a bit younger back then. It had 150 megahertz. That was blazingly fast. And then it was a RISC processor, but it was emulating a CISC instruction set. This was really interesting because this allowed for new performance optimizations. Also a huge level 2 cache, 256 kilobytes. Even if you buy a processor today, it will have 256 kilobytes level 2 cache. Not exactly the same because it's per core, but of course, the basic design is from that time. And also introduced their branch prediction and out-of-order execution. This is awesome for performance. And also, if we look at the future is going to be even faster and even better. Looking at the Apple iPhone X, it now has 16 kilobyte pages, and this allows to have 128 kilobyte caches.
Daniel, not so fast. I am Moritz, Spectre of the past.
What are you doing here?
I'm here to tell you that you're all wrong. All about your performance. It's not what we want.
Everyone wants performance.
Yeah, but not at the cost of security. And that's the big issue. You always want to improve things, build better CPUs, faster CPUs, and that's all you care about. But that's a big issue. And I've told you that in the past all along, but you weren't listening. So I will repeat it again. So, assuming we have bug-free software, which of course is not the case nowadays, but assume you have no error in your code. This still doesn't mean you have a safe execution with the code on the CPU, because transformance information can leak through the underlying hardware, which you are building and making faster and faster all the time.
But it's just the problem that software developers are writing bad code, right?
No, not really. It's just the hardware. And as an attacker, we can exploit that by looking at the side effects this is causing. Because the power consumption could increase depending on what you're doing, or the execution time of the algorithm, or the CPU cache, as I've told you many times before, can leak information on what computers are doing.
You did not tell me that before.
Oh, I did, many, many times, and we will see that. Maybe you will remember it. But more importantly, before we dive into that, we need to understand the difference between architecture and microarchitecture. Because the instruction set architecture, like x86, ARMv8, is just an abstract model of how the computer is working. And under that, there is the microarchitecture. And the architecture itself just serves as an interface between the hardware and the software, so that we can write a code once for x86 and let it run on different microarchitectures, which is the actual implementation of the architecture. Like AMD Athlon, AMD Ryzen, Intel Core, Intel Xeon, and so on. And they all differ, because they contain multiple microarchitectural elements. And these elements are improved in order to gain more performance. So those architectures that we've seen, they differ, some are faster, some are others, and this is the cause by those elements, like caches and buffers, or branch predictors, which you mentioned earlier.
But this is good, right? Get to the point. What is your point
Yes,
here?
this is really good, because they are transparent for the programmer. So you just write the code once, let it run, and on some machines it's faster than on others. But the big issue is these optimizations that you have, they introduce a side channel leakage, which we can exploit.
Really?
Yeah, we will see that. But you're only talking about performance, and I also optimized something myself. So I really like to cook for people, and this Christmas I also cooked something. And I was thinking, I want to cook some vegetables, so I was looking and figured out, oh, I don't have any tomatoes at home and no paprika. So I needed to go to the store to buy them. Then I got home, started cutting them, and figured out, damn, I'm also missing the spinach. So I needed to go to the store again. And this is annoying, because this takes a lot of time so that you can come back and finally start really cooking. So I invented something inspired by computers, what you can do to improve this. And I invented the food cache. And this is incredibly nice, because now you can just go to the store, buy everything, put it in the fridge at home, in your food cache, and whenever you want something, you just go to food cache, and you're much faster than going to the store. This is incredible.
Did you just explain processor caches by comparing it with shopping?
No, I mean, it's a bit related, but it's obviously something different. But processor caches, we had that. I already told you that. Do you remember 2 years ago at 33C3?
I was not there.
Yeah, but you watched it online, I guess. So I had a talk there with Clementine Maurice, and we talked about what could possibly go wrong if you insert an x86 instruction at this placeholder. And we talked about your CPU caches. So imagine you have a line of code with a variable I. And the first time you access it, the CPU will take a look in the cache and see, oh, it's not in the cache, so we have a cache miss. Then the CPU needs to ask the main memory to serve this address. So we have a memory request, which goes to memory, it will respond, and transparently load the value into the cache. So the second time we want to access this address, it's already in the cache, like my food cache when you go shopping. So it's much faster. So when we have a DRAM access, the overall execution time is slow. But if it's in the cache and we don't have a DRAM access, it's much faster. And this is very nice, because when we measure that, we see for cache hits, we are really, really fast. But for cache misses, it's slow, because we have to go first to the main memory. And this you can exploit. And this is where you need to listen very carefully. So for instance, we have the flush and reload attack. So imagine the attacker process on the left and the victim process on the right. And they both use the same shared memory, which means if the address is cached, it's cached for both processes. Now, the attacker can use the unprivileged flush instruction to remove this address from the cache. And then the victim is scheduled. And now the victim can either access this address or not. If he is accessing the address, it will transparently load it back into the cache. And now, what the attacker can do, he can measure the next access, like we've seen in the histogram, and figure out if the access is fast, the victim in the meantime has accessed the address, and if it was slow, he didn't access that. And by that, he can spy on the victim.
You really think you can leak any meaningful information with that? I doubt that.
Yeah, you can build powerful attacks, because by just looking at cache hits and cache misses, you can leak AES keys from the cache. You can leak keystroke timings from the cache. You can covertly send data from one process to the other. For instance, you have an Android application with no privileges, and it sends data over the cache to the other application, circumventing the permission model. And also you can attack the browsers, you can attack virtual machines in the cloud, you can attack trusted execution environments, and this is really nice. And you still don't care? You don't believe that?
Yeah, I think that is just timing side channels. That's
No, that's a real issue. Look, for instance, we have an Android application on the left and our spy process on the right. And when the user types something like hello, our attacking application can monitor the keystrokes and the exact timings. Even if you delete a word, it will detect it. So it knows exactly when you typed something, how long the word was, and by the inter-keystroke timings, you can recover the words.
But you don't know what I typed.
No,
go off
listen.
the stage. This is my stage. I
Learn
want to talk
something.
about performance. Let's talk about performance. So that's why I'm here. And I was talking about the iPhone, but there are also other very interesting mechanisms here. For instance, Intel, on their newest processors, introduced a deeper out-of-order pipeline. This is better because it has more parallelism. And I will explain out-of-order execution to you. And I will just take the same analogy that Moritz just used, cooking. Because that's actually something that happens to me from time to time when I cook. I don't do it very often, but I do cook from time to time, for instance, cookies. And I start with putting all the ingredients on the table, and then I have to mix them and stir them a bit. And then I form these small bowls here and press them flat, and then they make nice cookies later on after I put them in the oven. And of course, it's better to have cookies with chocolate. And so I also melt chocolate and then dip them into chocolate. Well, and then they look really good and really, really tasty. You have to turn on your microphone. Did you ever do this before?
Yes, it's on.
I mean.
I don't know. Should be on. No.
So, anyway, very tasty cookies. I like them.
Yeah.
The
Does it work?
computer,
Ah.
to some extent, does the
Whoa,
same
whoa,
thing.
whoa, 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 whoa. Now you're surprised, right?
I'm
So-
not sure what's going on with you. Who are you, anyway?
Look at me. I am the Spectre of the present. And I know you really, really like your performance optimizations. And you build them into computers. But do you know that you have issues with that? So we have the same thing you explained in cooking. You have this work-job balance. You mix things together, your performance optimizations in computers and at home, and it's all the same for you. But if you do that in computers, it has real issues there. So if I look at a computer, I have a simple code like that with some code lines, and some of them, they have dependencies, and some of them, they don't have dependencies. So I can do them in parallel. And this is exactly what a computer does as well, as you did with the cookies. So if I look deeper down in a computer, we are here still at source code level, but if I go down in the computer, then I have this out-of-order execution engine that uses the instructions. It fetches the instructions of my application and decodes it. And after it decoded it, it dispatches it to the back end and it executes it. But it can do that in any order if there are no dependencies. Then it just executes stuff in any order, not the order I have in my application. So it does the same
I
we
was
did with
just
the
about
cookies.
to explain that, and I don't see any problem with that.
Yes, because you're so focused on performance and not on security. See.
Like
let's
the
do an-
security problems that the Spectre of the past explains?
No.
No one cares
That was
about
the
that.
past, but now we are in the present and things get worse. So look at this simple experiment.
That won't compile. Or it won't.
Oh, it will compile.
But it
Where
will
did you-
crash. It will crash.
It might crash. I mean, my compiler was not so happy about that. It says, that's a statement with no effect, does nothing, it's just a null, and I dereference it.
Did you even
don't
learn to
assign it.
program?
Yeah, you taught me. So the compiler was not happy, you're right. Also, because good things in coding, use static code analyzers, was also not too happy about that. Says, as you said, it's a null pointer dereference. This will definitely crash. Why are you doing that? And this is true. You're right. The compiler is right. the static code analyzer is right, they're all right. But still, it's an interesting element. So we all agree it will crash in the first line. ID reference, an invalid address, program will crash, that's it. Next line will not be executed, right?
Yes. I don't know why you're
So-
writing nonsensical code
So
here.
I would never, ever access this memory here at the location, because it crashed before. And then I used the techniques of the Spectre of the past that you don't like. And I executed that application, it crashed. But then I looked at the memory and looked what part of the memory was actually cached. So we know that it was accessed. Whoa, it was accessed. So
yeah, but
this
this is
line that
just
was
out
not
of order
reached,
execution. This is fine.
this is fine. There's an exception before that. That shouldn't be fine. The exception was thrown
Yeah,
afterwards.
but this is just out of order execution. Nothing to worry about here.
Okay, if you think so. So still, we see some traces of that out of order execution. So that might not be that innocent as you think, because we can see the results of that in the cache, even though we shouldn't see it, because it should never have happened before. So let's call them transient instructions. They did something, they disappeared afterwards, but they left some traces. And using them, we can indirectly observe the execution there, what's going on. So even though there's a point where we shouldn't see anything. So if we now look at loading addresses, now we had a null pointer, right? Not interesting. But if you remember operating systems, how things work, if you want to read something from the memory, we have a pointer, we dereference the pointer. Then the memory management unit will check the permissions bit. Can we actually access this address? Does it belong to our address space? Is it part of the kernel? If everything is fine with the permissions, then the CPU is happy and we can read the value at this address, as it's supposed to be. If something is not that fine because we access an address which we are not supposed to access, then we die as an application. So this is also fine. But let's extend the experiment and have the same thing, but now don't access a null pointer, but access some inaccessible address, some kernel address, some address which we are not allowed to read from. And we do the same thing. We read the data from the address.
Yes, but now
Yes,
it cannot
yes.
execute this out of order because it depends on this one.
Oh, you think it has a data dependency, it
Yeah.
stops there, doesn't use
Yes,
the value it read.
exactly.
Okay. So, but we might still check whether anything of the array is cached.
Go ahead.
Oh.
Oh.
Oh, so your out of order optimization reveals data. So it actually read the data, which it was not supposed to read,
That should not happen.
used it as an index in the array, and cached that part. Afterward, yeah, it crashed, so it didn't get the value, but I can see it in the cache,
Yeah, that's not good.
what the
That's
value
not
is. So sometimes it doesn't work what you optimized there.
good. Okay, but maybe
We can run that also in a loop for multiple addresses. Oh,
that's leaking
no,
data really
that's leaking
fast.
data from the kernel.
Okay,
Super
that's
bad.
something.
That's not supposed to happen. That's
Yes.
not a performance optimization. We call that meltdown.
Okay, but
But-
can we do anything against
But
that?
that's not an issue, Daniel. I told you before, like with the attacks, I also told you about countermeasures. But you never listen because you only care about performance. And I'm really sorry for you. Maybe you will learn for the future. So, as we've seen from the present, the kernel address that we have in the user space, they are our problem. So, why don't we just take the addresses from the kernel and remove them if we do not need them? Because the user accessible check in hardware is not reliable.
Okay, that sounds good.
Yeah, so what we just do is we unmap the kernel whenever we are running in user space. So the kernel addresses are then no longer present. And which means memory, which is not mapped at all, cannot be accessed at all.
Okay, that's good. So you're saying the problem is basically solved?
Yeah, so if we change the operating system, so previously it looked like this. We had the user space, we had the kernel space, and the memory isolation you can illustrate as a wall in between. Because it would be an issue, of course, if you could just see what the kernel addresses are. But now this wall has holes in it. So what we do now is we change the perspective a bit. So when we're running in kernel mode, everything is mapped, everything is fine. But whenever we're running in the user mode, the application can still mount the attack, but behind the wall, there's nothing there. So it cannot leak anything.
Ah, that's perfect. That means that the problem is solved.
Yeah, absolutely.
And we can
If you
focus
apply
on
the
performance
patch.
again. So off the stage with you, and I can continue with my performance talk.
Daniel.
Oh God, no. I mean,
I came here all the way from Belgium to tell you that you're wrong.
I feel I'm haunted by ghosts.
Yes, you are. So did you think about virtual machines in this picture? Let's throw you a new picture. Virtual machines are everywhere, Daniel. They're not just virtual. They store your data in the cloud. And since virtual machines are everywhere, Intel decided to make them super fast. So we have seen page tables before. What happens in a virtual machine when you access memory is that the processor first translates it to a guest physical address. And after the guest physical address, which is in the virtual machine, is translated in a second level to a host physical address, we have the nice performance optimization of the cache, just like the food cache. If it's there, we access it. So far, so good. But did you think about what happens when we access a page that doesn't exist? A non-present page in the virtual machine.
Oh, they wouldn't do that.
Sure, let's see. So it's not present. And we will never translate it to a host physical address, right? Doesn't exist, doesn't make sense. So far the processor is right. But since it's super fast, it's optimized for the fast case, and it will access the level 1 cache without the address existing. So something horrible can happen here. You can read any address from the virtual machine as if it was a real address, because the L1 cache doesn't care about virtual machines. It's super fast, close to the processor. So what do you think about that?
Okay, that's a problem, but okay, so this is just the meltdown problem. But maybe if I don't use virtual machines, I don't have the problem. So maybe you can go off stage because
We will see later, Daniel.
Yes, no, I hope this is not that. Intel also said they fixed it, right? I don't have to care about that. I saw this Intel announcement. All of this is fixed. The new processors are fast and secure. So let's continue with the performance talk I wanted to give here. So, as I said, Intel introduced more ports, more parallelism, larger reorder buffers. This is really, really good because things are getting faster. And let's also look at AMD. AMD, in their most recent processor designs, introduced a perceptron-based branch prediction mechanism. This is great because the branch prediction gets better. And to explain branch prediction, we have to take a step back again, maybe think about something where we have a real-world case, where we have to predict something. And something that you might have wondered is, how does Santa Claus get all the presents prepared in time? So let's start with this one. You probably know this comic. Who does sudo report these incidents to? Well, there's the nice and the naughty list. And only the nice children or administrators, in this case maybe, get presents. So the idea here is that Santa Claus wants to get rid of bottlenecks, right? So that Santa Claus can prepare the presents and then save some time, basically be more performant. And the idea is Santa can just use the naughty and nice list from the previous year. That's great, right? And then Santa can just start preparing the presents all year long and then save some time later. In the end, just the day before Christmas, Santa just has to check the predictions and then see which ones were correct. And the ones which weren't correct, Santa has to throw away the present, or maybe quickly prepare some new one. Maybe then it's not so good as the other ones. So if you have some incentive to be nice all the time, of course. Yeah, but basically, Santa can just throw away the wrongly manufactured presents. And because Santa does that throughout the year, Santa only has to work a bit all the time. and the remaining time is free time. You can go skiing. Great.
Whoa.
Oh, no,
you
not-
don't learn anything from your mistakes,
Why
right?
are you on the stage again?
Don't you see the issue here?
There is no issue. Senna has free time.
Besides
He's
producing a
having
lot of
fun.
waste, besides producing a lot of waste from your wrongly manufactured presents, you also give away information. Imagine someone looks at the trash and learns who was nice before and became naughty the last year.
So you're suggesting that I look through the trash at the North Pole? I would have to get there, right?
Sure, but
No
we are
one can
talking
get
about
there.
computers, and we don't have to go to the North Pole to do something with computers. We call that the Spectre attacks. And we do something really, really similar in our computer. It's a performance optimization, as you've said. So if we have some data in memory that we can access and something next to it which we are not supposed to access, then we usually have some bounds checking there. We check whether the index of the array we want to access that is still in bounds, so we don't go out of bounds. Otherwise, we have some problem in our application and it might crash, it might do something weird. So what we usually find in our applications, if we have some index that goes into the array, and then we retrieve the value there and use it in a subsequent calculation to look something up in a table, for example. It could be a font file, we get a character out of the array, look it up in the font file, it's in shared memory, and this will be in the cache then afterwards. And of course you want to optimize things. So there's only a yes-no decision here for the condition. So either the index is allowed to be used, it's in bounds of the array, or it's out of bounds. So the CPU starts having, has a predictor there for the conditions. And it will happily speculate what will be the outcome. So we start with the index 0, it's a valid index into the array. CPU has no idea what's going to happen, speculates, 0 must be larger than 4, does nothing, but it turns out it's wrong, and the CPU has to execute the other side of the branch. But this also updates the prediction. So it knows the last time this comparison was true, so it will do the same again for the next comparison. So if I go for the next character in the array, then it's still valid, and we know that it's true, and the CPU thinks, oh, it was like that before. It might be true again, so it will already speculate, use the data, do some calculations.
And that's good, because now it's fast, right?
Now it's fast, because it already speculates and has that correct. And that works. But what if someone decides to pass an index which is out of bounds, which would refer to memory that you should not access? So the CPU still thinks, it was always the case that this is true, so it must be true in the future. So it was always the same, so why change something? It's a lazy CPU. And it speculates, and it does something based on memory it should not access, but it still accesses that, puts things in the cache that correlate with the secret data, which is not supposed to access, and we can again do the cache attack and see that in the memory. And it says, oops, sorry, mistake. I had to execute the other path, but we still had this transient instruction there that leaked some values to the cache. So we still get data out with that. And we can continue that, of course, and leak all the secret data, because the CPU is not so fast in updating the prediction. And this is not only true for ifs. This is also true if we have C++ and we have function calls, and we have classes and some polymorphism, and that changes. So it can have different methods, fly or swim the animal. If the animal is a bird, the bird flies, so it executes that. If we change the animal then to a fish, it knows it flied before, so it has to fly again. It's a flying fish, but it's of course wrong. So it executes the wrong function. It should have executed swim. Again, a wrong prediction, executes things, accesses data, which the CPU is not supposed to do.
But we do have the Kaiser patch, right? So we don't have to worry about all that.
But this is all in the same process. This is all in the same process. So, yeah, and this is also for returns. So if you have function calls to the same function and they have different runtimes there, then the CPU also predicts where it's going to return, to the one side or to the other side. We can manipulate that and then return to wrong destination and execute code there which we are not supposed to execute. Just for a
But-
short period of time.
Yes, all is
falls back.
unrolled.
All is unrolled.
Yes, yes,
But you know the cache.
yes.
The
But
Spectre of the past told you about the cache.
getting back to the Kaiser patch, we had Spectre and Meltdown, right? And both are mitigated by the Kaiser patch. Is that correct?
No. Just the Meltdown. Just the Meltdown, not the Spectre. Spectre never accesses data that's invalid to access, just what it's not supposed to access.
Okay. Okay.
Yes. So if you're looking about Meltdown versus Spectre, we have some operation, we have some prediction, and we predict some control flow or data flow here for Spectre. And as soon as we start predicting the control flow or the data flow, we're not sure whether this prediction is correct, so there's a transient execution there, it might be rolled back. So nothing wrong happened here.
But the same happens for Meltdown, doesn't it? It speculates somewhere.
At some point, for Spectre, it decides, oh, that might be wrong, and it flushes the pipeline, and that's it. But everything was fine so far. For Meltdown, it's a bit different. You still have the operation.
Yes,
You
so
have-
it looks the same.
Then we have some instruction loading data, for example. We have this data dependency we've seen earlier. And then we have an exception when loading the data. So because we did something we're not supposed to, we get an exception in the CPU. And from the point of the exception, we know that nothing after that should really happen anymore. We have to roll back if we do that. So we also have the transient window here. And normally, if you have an exception, you should not forward the data generating the exception.
Yeah.
Because you're not allowed to
Yeah.
do that. So if you throw that away and continue, it might be fine, because you don't leak the actual data. But the Meltdown here is an optimization to not have to implement the trash can here. So you jump over that, and you forward the data of an exception to another operation there. So it's a difference. This is an actual performance optimization that turned out to be a vulnerability.
But then in the end, everything is unrolled again, right?
Yes, but the cache.
But Intel
Cache.
said they fixed all of that. I read the announcement, and you are telling me about fixed vulnerabilities off the stage with you. I want to continue with my performance talk. So I was just speaking about the Apple, the
Daniel,
Intel, and
you still haven't learned anything. We have wasted now half an hour telling you stuff, and you simply don't care. And you know what? Stubborn old men don't get any Christmas presents. So you always talk about you want performance. So you probably heard about Intel memory protection keys. Memory protection keys, you can assign one of those keys to a group of pages, and they are simply identified by 4 bits in the page table entry, and they say which region they belong to. And this allows for a quick update of access rights, because you don't have to
which
flush
is
TLB.
good for performance.
I thought you might like that. But we also have the problem here that those protection keys are lazily enforced. So you get a page fault, and the same happens that we saw in the case that the Spectre of the present showed you. So using a flush and reload attack, we can still recover the protected value that is forwarded to the transient instructions.
Okay, but this is also mitigated by Intel's patches. Intel released those patches. All of this is not relevant anymore, right?
Okay, then so let's move on. We also have another thing. We have on x86 a dedicated instruction that raises the bound range exceeded exception if you access something that you're not supposed to access, that is protected.
Yes, I also know that. Yes. What about
Yes.
it?
Yeah, we also have here the problem that the data is used in the transit execution. So you might see a pattern here, but okay, maybe you don't. So our attacker can still access the cache line, or can see which cache line was accessed and recover the data that was used. And the nice thing about this, because you might have seen, you read the Intel announcements, you might have also read the AMD announcements, that they are not vulnerable to all this. And
Yes, yes,
this
yes,
is also
the code.
highlighted in the patches. Yes, so if you're on AMD, we don't care in Linux.
Yes.
But the problem is here that this is actually the first Meltdown type attack on AMD that we've seen.
What, this works on AMD?
Yes, it does. And we have all these different attacks that we have seen. We have the Meltdown US that the Spectre of the present showed us. That works on Intel, ARM, AMD, and some of those we were able to show in our paper that they do work, they do not work, and the ones that are highlighted by the star, we are the first to show them. And you also want to know about defenses. We looked at them and we came up with defenses that we can categorize in 2 categories. The first one is that maybe if the data is architecturally inaccessible, maybe it should also be microarchitecturally inaccessible. Or in the second category, we can simply prevent the occurrence of faults.
So, you want an example of the first category? Let's look
Of course.
back at the virtual machine attack, the Foreshadow attack. So we call it here Meltdown P, and as the Spectre of the future said, we try to make data inaccessible. And this is actually a very elegant fix that got pushed in the Linux kernel. So basically, let's just clear out the physical address of any page table entry when we unmap it. Very nice and easy fix. You can't reach any data if it doesn't reside at address 0. However, with the virtual machines, things are a bit more tricky, right? Because we don't trust them. So turns out we can do nothing but flush the cache. And here we have a bit of a problem, because the Spectre of the past told us that caches are super important for performance, and we don't really like to flush them. So it's a bit tricky. Most Linux distributions don't flush the cache here, and that can give us real problems.
But we have seen he always denies that Meltdown P is a problem. So can you maybe convince him in a way?
Let's have a
It's a
look.
problem?
Let's see if we can do that. I have a piece of code here, which I don't really trust. It was written by Michael, the Spectre of the present, and usually
We know
when I
that
don't...
he can't write code, right?
Yeah, let's see. Because usually when I don't trust code, I put it in this nice virtual box environment. I like virtual machines. Let's fire up one. If I can get the mouse to work. Oh, it's weird code written by our Spectre from the present.
Oh, but is this the fully
So-
patched virtual machine?
Oh yes, it's an off-the-shelf Ubuntu distribution. And let's see if I have some secrets here as well.
So if it's fully patched, then nothing will happen, right?
Oh, we have our Santa, who has a nice list manager, protected with a password. Okay, and the weird code is starting up.
It's printing dots. I don't know whether that means
It's totally untrustworthy code, saying all kind of weird things. So let's give it some input. I just typed here, reader. Typo?
You have 2 A's.
No typos.
Oh no, it's weird code. Yeah. So now you can see a real hacker at work. We're just missing the progress bar. No, it's a... Okay.
Okay, so the attacker code is running. Start to type something.
Okay, so maybe anyone could guess what the password is of this password manager. Any guesses what we should enter here? Some? Linuxtage.
that is not a secure password. I cannot recommend that.
I think you had the wrong address. Okay. Let's see. We need some Jeopardy music. There was a wrong address here. Because for convenience reasons, we let the password manager tell the address where it stores the password, so we don't have to look for it. Okay.
Okay.
Let's see if it now works.
Of course
The
it doesn't
Linuxtage
work
was?
because Intel said they patched this.
Oh, there's something coming. Whoa, it's a real-time keylogger from within a virtual machine. Nice.
Wait, but this was a fully patched machine. Why does this still work?
Because it's not patchable.
But Intel said they patched it.
Yes, but they didn't say everything. You can only patch it if you disable hyperthreading. And you wouldn't do that, right?
So let's get back where we were. We have seen now so many different things, and it's a little bit confusing now. So we cannot classify all these attacks that we have seen. So let's start with our transient cause. We have Spectre-type attacks, which always start with prediction, like the Spectre of the present told us. And we have Meltdown-type attacks, which require a fault. And we have also seen all these different versions, Spectre PhD, BTP, simply name them based on which microarchitectural element they exploit. But we can move further than that in our classification, because so far most of the research has shown that we can attack in the same address space in place scenario. So we actually mistrain the branch at the exact location that we later on want to exploit. But we were also able to show that we can do this on an alias branch because the element is only indexed by a subset of the virtual address bits. So we call this the same address space out of place scenario. But it gets even worse than that because the branch predictor state is actually shared between on a logical on a hyperthread. So we were also able to show that we can do this, the mistraining, in the same address but in a different process, which allows much more powerful attacks. And as before, we can also able to show that this is possible with an aliased address. And we can also take a look at all the different vulnerable vendors. We have Intel, which is pretty much full support of all vulnerabilities. ARM, we were able to show some of them work and some did not work in our experiments. And for AMD, the same case as for ARM. And we also saw a bit of a few defenses, but we have the best defense ever. We call it the trilling template. Because we are seeing...
Joke, right? That's just a joke.
Well, it would be effective. Because if you disable the whole CPU, there's nothing that's going to leak anymore. But on a more serious note, let's look at Spectre defenses like we did with Meltdown. We have those in 3 categories. In our first category, we can mitigate or reduce the accuracy of our covert channels. Because if we can't recover anything from the cache anymore, we should be safe. At least that's what's claimed so far.
Yes, yes.
In a second category, we can just mitigate or abort speculation whenever it happens. So that should also help a lot. Or we can simply ensure that the secret data cannot be reached anymore, because if you can't access anything, that's much better. But when you take a look at all the different microarchitectural or all the different defenses, you can see that we have so many different microarchitectural elements, and most defenses only take a look at very few of them. So you can just substitute one for the other and it still works.
Oh, that's not good.
No, that's not good. But let's take a look at some of those in a little bit more detail. Site isolation. The idea behind this is that we execute each site in its own process. And this limits the amount of data that is exposed because you have only access to the data in your own process.
Yes, and that's what they deployed in browsers, right? So it works.
Yes, that's, so far it's the default in Chrome, and Firefox is also working on it. Intel, you always reference their announcements.
Yes.
So you have probably seen that they recommend inserting instructions that stop speculation. So we
Yes.
call them serializing
Yes.
instructions.
And that also works.
Yes, and they say, let's do this after every bounce check. But this is pretty bad for performance. And
So if you look at all these attacks, then basically you will have something like this.
Yes, that's
Oh,
what
that's
we
bad.
came up in our paper. So we have many different attacks, and it's not looking very good so far.
So red means that they actually work? Oh, that's bad. That's really, really bad.
Yes, all that are in red, we were able to show in working proof of concepts.
So, thought I had a weekend and I'm retired because I'm from the past and you haven't learned anything and the microphone is also not working. But what we've seen in the entire talk that microarchitectural attacks have been ignored for many, many years. And you didn't learn anything. Because we had attacks on crypto. We leaked keys.
But for crypto, the software should be fixed. It's not an issue, right? The more dangerous thing is we have attacks on ASLR.
ASLR is broken by design.
But we also extracted keys from trusted execution environments. That's a real problem, right?
Well, this is not within the threat model of anything. So, but we have also seen rowhammer attacks.
Yeah, but it only affects some cheap models like
Okay,
80%.
so dear ghosts, I think I understand now that for years we solely optimized for performance, and maybe that was not the best decision. I give you that. But what do we do now?
So we have seen optimizations always come at a cost, so we have to think whether we really want to optimize things, also whether we want to defend against that, but because this also comes with a cost. And yes, you have seen, this will keep us busy for quite some while now.
So
we'll
you're
see.
thinking there will be new attacks?
There will be
Oh,
new
God.
attacks and more powerful ones. So yes, go back to sleep.